Dear students, I welcome you for the today's lecture. We are going to understand the frequency response technique in the subject of our process control. This is related to the stability of the control systems. Till now, we have discussed the route array and the root locus diagram. This is the third technique that is going to give the details related to the frequency response technique. The Bode plot that is also to be carried out to understand the analysis of this frequency response. Now it is basically to design the control systems using the frequency response. So frequency response, that means our output of the output for a sinusoidal input, that will be also in a sinusoidal form, because most of our systems related to the chemical engineering, they give you the response in the sinusoidal manner. So it is more essential to study or more essential to focus on these sinusoidal systems where you get the response in a sinusoidal manner. So it is better to give the detailed understanding related to the response of these control systems where you get the sinusoidal output. So using the frequency response is based on the characteristics of frequency response analysis. So basically we are going to study the analysis of this frequency. Frequency is with what amplitude it is going to move, it is going to fluctuate. So frequency response analysis determines the output sinusoidal wave when a linear system is subjected to the sinusoidal input. It is what the system is subjected to a sinusoidal input, and we are going to study this output, which mostly you will get in a sinusoidal manner. Now, this is a graphical method to study the frequency response. So it helps to understand the stability of a control loop. Then it gives you the optimum values for your K, tau I and tau D. And third thing, that helps to consider the output changes as the frequency change from 0 to infinity. So what is the effect of the frequency change, that is also studied in this frequency response technique. So this is the additional thing, that the output changes as the frequency is changed from 0 to infinity. You will get to study in this frequency response technique. There is a zero frequency corresponds to a situation where the input changing is infinitely slow. That means very small variation has been observed due to the zero frequency, and thus change occurs over an infinite length of the time. बहुत ज़्यादा slow fluctuations आ रहे हैं. So that is called a zero frequency, and it is corresponds to the steady state condition where there is no change in the parameters with respect to the time. That is what the steady state condition is. Now we have already studied the frequency response of the first order element as well as second order element, where we have taken the Laplace transform, we have applied the forcing function to the first order system. Then we have simplified that and obtained the yt as a response, which you will get as a omega tau upon 1 plus omega tau square e raised to minus t upon tau plus a upon root of 1 plus omega tau square sine of omega t plus theta. This is your generalized response for the step for the sinusoidal change with first order system. Then at steady state, that means t tending to infinity, his first term that will change to 0 and the remaining term will be only a upon under root of 1 plus omega tau square sine of omega t plus theta. And where we have calculated the amplitude ratio, that is nothing but the output amplitude upon the input amplitude, that you will get a will get cancelled. So you will get 1 upon root of 1 plus omega tau square. This you will get it as the amplitude ratio. Besides that, we can also in case of a second order system, we have also calculated the yt response, then yt at steady state, amplitude ratio and phase angle. So now this is the method of a frequency response for the first order systems. So we are going to consider the first order transfer function initially, that is gs, which is equal to the k upon 1 plus tau s. Now here we have to substitute s, which is equal to the j omega. Substitute s will be equals to the j omega. That means we are writing in a complex form. That is, we are converting the transfer function of a system into a complex number system. We are converting the transfer function of a system, whether it's a first order system, second order system, or the transportation lag, whatever the transfer function is there, we are converting that transfer function into the complex number system by substituting s, which is equal to the j omega. So this is the first step we have to do. That means we have converted the transfer function, which is in terms of the s, into the complex number transfer function, that is j omega. So s, that we have substituted as s as j omega. So this is the transfer function which is in terms of the s. Now the transfer function which is in terms of the j omega. K is your steady state gain and t is your time constant for the first order system, as it is the first order equation. Now next thing is to rationalize the denominator. For that purpose, we are going to multiply and divide by 1 minus j omega tau. We are multiplying and dividing by 1 minus j omega tau. So this is what 1 minus j omega tau, that is multiplied, and this is 1 minus j omega tau, that is divided. This is we are doing it to do the rationalization. So then simplifying that, so I, which is nothing but under root of minus 1, under root of minus 1. So you will get I square, j square as minus 1. So you will get this system, that is k into bracket 1 minus j omega upon 1 plus omega square tau square, where j square, which is equal to the minus 1. Then we are going to separate this 1 upon 1 plus omega tau square and omega tau upon 1 plus omega tau square into the j. So this is a complex number and this is our regular root. So we are going to have the real part of the complex number and the imaginary part of this complex number. Real part, it is defined as m, which is equal to 1 upon 1 plus omega tau square, and the imaginary part of the complex number n, which is equal to minus omega tau upon 1 plus omega tau square. From where these are coming? These are coming from, this is our two parts, the real part and the imaginary part. K, that is, can have the value of 1, which we are assuming that steady state gain as the value of 1. So I can write this as a real part of a complex number and the imaginary part of a complex number. So this is written as m plus nj. So on the considering the complex plane, I can plot on the complex plane. So m on the x-axis and n on the y-axis, that is your imaginary axis. So you will get or form a triangle OAB. Then your hypotenuse OA, that is nothing but the summation of root of AB square plus OB square. So that is OB square plus AB square, which is nothing but m square plus n square, and that is same as your real part square plus imaginary part square. So this figure itself shows that if you want to calculate the value of OA, it is nothing but your AB square plus OB square, that is your imaginary part square plus real part square under root of. So OA is root of real part square plus imaginary part square. And similarly, so we have substituted the value of m and n. So OA, that comes as 1 upon root of 1 plus omega tau square. So this is nothing but your amplitude ratio. Amplitude ratio is 1 upon root of 1 plus omega tau square. So amplitude ratio, that is defined as under root of real part square plus imaginary part square. Next is your theta. The angle made by joining with the origin is theta with a real argument of for g of j omega transfer function in terms of the complex number. So tan theta, that is nothing but perpendicular upon base. Coming to the same figure, this is the theta angle that is made with the real axis. So your tan theta is nothing but the perpendicular upon the base, that is AB upon OB. AB is your imaginary part upon OB is your real part. So this is what the tan theta is equal to perpendicular upon base, which is equal to the tan inverse of n upon m. So theta, that comes as minus omega tau. That is nothing but the imaginary part square upon real part square. This is the perpendicular upon base. Perpendicular is your vertical line, so it is on the imaginary axis. Then base, that is on the real axis, so it is the real part. So we have first converted the transfer function into the complex number by substituting s, which is equal to the j omega. Then second thing, that we have converted to rationalize the number by dividing and multiplying by 1 minus j omega tau. Then separating the two things, that is your real part and the imaginary part. So real part and imaginary part, the OA, that is nothing but your hypotenuse, that is nothing but the amplitude ratio. So this under root of real part square plus an imaginary part square, that comes finally as the amplitude ratio, which is equal to under root of real part square plus imaginary part square. So similarly, we have also defined the tan theta, which is nothing but the tan inverse of imaginary part upon the real part. So theta and amplitude ratio both are defined in terms of the imaginary part and real part. So every time whatever the numericals or whatever the derivations correspond to the frequency response technique that incorporates the use of j omega, where s that is substituted as equals to the j omega, then separate the real part and the imaginary part. So because all the formulas that is related to the amplitude ratio and the phase angle both incorporates the real part and the imaginary part. So this is very important that first, for any transfer function you have to substitute s, which is equal to j omega. That means we are converting the transfer function of a system into a complex system. Converting that into the complex system, then for rationalizing, we are multiplying and dividing by the proper term. So, and then separate the real part and the imaginary part. That will be a standard procedure. So every time we have to follow this procedure only. The same procedure now we will follow for the second order system, for proportional controller, for proportional integral controller, for proportional derivative controller, proportional derivative and integral controller, and for transportation lag problems. In the first part, we'll only see the how the imaginary part and real part that is obtained, and then we will move next to the Bode plot, Bode diagram plotting actually. It requires the understanding of this amplitude ratio and the phase angle, and that is why in the first part we are primarily considering the how to calculate the amplitude ratio and the phase angle for different systems. Then we are going to study the details related to the numericals, how to calculate the real part and the imaginary part. Now coming to the second order system, that is nothing but 1 upon tau square s square plus 2 phi tau s plus 1. This is our equation corresponding to the second order system. Now this equation is in terms of the transfer function s. Now substitute s, which is equal to the j omega. So substituting this s in terms of the j omega, so s square, which is equal to the omega square j square, then s, which is equal to the j omega. So you will get 1 minus tau square omega square, 1 minus tau square omega square, that is j square is nothing but the minus 1. J square, that is equal to the minus 1. So this sign of minus 1 that will appear, plus 2 phi tau into the omega into the j. Now this is the return in terms of a complex number. So next thing is that you have to convert or rationalize this system. So for rationalization, you are going to multiply with this 1 minus tau square omega square minus of 2 phi tau omega into the j, and then separate the real part and the imaginary part. Separate the real part and imaginary part. So substitute s, that is equal to the j omega, first thing. Then you get this transfer function into the terms of the j omega. Then you have to rationalize it. then you have to rationalize that and separate the real part and the imaginary part. So that for obtaining the amplitude ratio, you will get the under root of imaginary part square plus real part square. So after simplification, by substituting the values of this real part and by substituting the value of this imaginary part, you will get amplitude ratio as 1 upon the root of 1 minus tau square omega square plus 2 phi tau s, 2 phi tau omega. Similarly, the phase angle is nothing but your imaginary part upon the real part, imaginary part upon your real part. So which comes as minus 2 phi omega tau upon 1 minus omega tau square. So similarly, what we have done is writing in terms of the m and n and then simplifying that, separating in terms of the real part and the imaginary part. So it's a real part square plus imaginary part square, which is equal to 1 minus omega tau square plus 1 minus omega tau square into square plus 2 phi tau omega whole square, and the imaginary part which is equal to nothing but minus 2 phi tau omega upon 1 minus omega tau square whole square plus 2 phi tau w tau omega square. So you can calculate the omega amplitude ratio and the phase angle. The next is the transfer. So this is related to the second order system. First we have talked the transfer function related to the first order. Then we are talked to the transfer function of the second order. First, initially we have converted the transfer function in terms of the complex number by substituting s, which is equal to the j omega, then simplifying that to obtain the and then multiplying and dividing to get with a suitable term to rationalize it, then separate the imaginary part and real part, then calculate the value of amplitude ratio and calculate the value of phase angle. So this is the standard procedure which we have to apply to every problem. Now apply it to the proportional controller. So the transfer function of proportional controller GC, which is equal to the KC, and by substituting the S, which is in terms of the J omega, so which is G of J omega, which is equal to KC. So this is purely a real number. So hence the imaginary component is the 0. The amplitude ratio is only the under root of Kc square. And tan theta, which is nothing but 0 upon Kc, which is equal to tan inverse of infinity, that comes as the 0. So this is the related to the proportional controller. Then next is the proportional derivative controller. So our proportional derivative controller, the transfer function gs, which is equal to kc into bracket 1 plus tau ds. Now substitute this s, which is equal to the jw. So gs, which is equal to kc into bracket 1 plus jw into the tau d. Then separate the real part and the imaginary part. So your component of the real part, that is nothing but your kc, and the component of your imaginary part, that is kc into the omega tau d, kc into omega tau d. So this is the real imaginary part into the j that is there. So after simplification, amplitude ratio, you will get kc square plus kc omega tau d whole square plus phase angle, which is equal to tan inverse of omega tau d. The next is the transfer function of proportional controller. So the transfer function of proportional controller gs, which is equal to kc into bracket 1 plus 1 upon tau 1 s. So substituting s, which is equal to jw, That means we are converting this transfer function in terms of a complex number and then separating the real part and the imaginary part. So amplitude ratio that comes as Kc under root of 1 plus K 1 upon omega tau 1 square. Similarly, the phase angle which is equal to 1 upon tan inverse of minus tan imaginary part upon real part square. So this is what the actual substitution we have done, and the amplitude ratio that comes as root of 1 plus 1 upon omega tau 1 square, and the phase angle is given as tan inverse of minus omega t upon omega tau 1. Next is the proportional derivative and integral controller, PID controller. So its transfer function GS, which is equal to Kc into bracket 1 plus tau ds plus 1 upon tau is. Then rationalizing it by then converting it into the complex number by substituting s, which is equal to the j omega. Then for simplifying, or you can rationalize it and separate it into the real part and the imaginary part. So j that has been taken out as the common, that means we have separated the real part and the imaginary part. The real part is 1 and the imaginary part is omega tau d minus 1 upon omega tau 1. So the amplitude ratio upon Kc, which is taken to the left hand side, which is equal to root of 1 plus omega tau d minus 1 upon omega tau d, and the phase angle, which is nothing but your imaginary axis upon the real axis.